Today I'm going to be going over matrices. So what's a matrix? Well, I could have this, just a set of numbers. I could have this, another set of numbers. I could have a bigger matrix. Another set of numbers. So how do I classify each of these? Clearly, each of these matrices are different. Like this one's 2 by 2, this one's 2 by 1, this one's 3 by 3. Well, this is exactly how I classify these matrices. This is 2 by 2, 2 by 1, and 3 by 3. How did I come up with these numbers? Well, this first number is always going to be the number of rows. This is the number of columns. So in this case, I'd have the first row, first column, or second row, first column, second column. This would be 1, 2, and 1. And this would be 3 by 3 matrix. So that's how I classify matrices. Now let's go over adding matrices. Last video, I'll just put adding right here. Last video we went over vectors, adding, multiplying, subtracting, and then computing or doing problems with them. Now I'll be doing matrices. So just a recap over vectors. I have a vector AB, adding it with the vector CD, and I have A plus C and then B plus D. Multiplying vectors, we had AB times CD, or the dot product of AB and CD. This gives us AC plus BD, or let's just call this vector V. This is vector W. This would just be the magnitude of V times the magnitude of W times the cosine of the angle in between these two vectors. So how do we do the same computation with matrices? Well, say I have the matrix A, B, C, D. Today I'll be using 2 by 2 matrix a lot. And I want to add it to the matrix E, F, G, H. Well, as we do with vectors, I could just add it to the corresponding number. So A plus E, B plus F, C plus G, and D plus H. This is our resultant, or our final matrix. Now what if I wanted to add A, B, C, D, and then just E, F? This would be A plus E, B plus, wait a minute, I don't have anything to add B with. So this is actually wrong. Well, what do we mean? What does this mean? This means that you always have to have a corresponding number when adding elements of a matrix. Now, what does this mean? This means that each matrix that you're adding needs to have the same dimension. So the matrices that you're adding have to have the same dimension. So you can see this is a 2 by 2 matrix, this is a 2 by 2 matrix, and we can add these two together because they have the same dimension or shape. And of course we get another 2 by 2 matrix. If I had a 3 by 2 matrix, I have to add it by a 3 by 2 matrix for it to be correct. And I'd get a 3 by 2 matrix as a result. And then say I want to add a 1 by 2 matrix and a 7 by 9 matrix. This is not possible, because clearly the dimensions or shapes of these matrices are very, very different. Now, what about multiplying matrices? So I have A, B, C, D, another 2 by 2 matrix, and let's multiply by the matrix EF, a 2 by 1 matrix. Just an important thing to note, this is a 2 by 2 matrix, 2 by 1 matrix. This is possible. Now you might be asking, what do you mean by possible? You're multiplying two things together. Of course it's possible. Well, with matrices, there's a limitation. Notice that these two numbers are the same. They're both 2. This is a quick test that this is a valid multiplication. You can multiply this together. If I had, let's say, I don't know, let's say a 2 by 2 matrix, and I want to multiply it by a 3 by 2 matrix, this will not be possible because these two are not the same number. Now, how do we figure out what the resultant matrix will be? Like when we after we multiply these two, what will the final matrix be? Well, we can look at these outside two numbers. 2 by 1. This will be the shape of our resulting matrix. Now, let's go on with multiplying them. How do we multiply this? Well, I can split this first matrix into two vectors, two horizontal vectors, AC and BD. And here I'm just going to multiply EF with AC. I'll just take the dot product. And this would be AE plus CF. AE plus CF. And my second element would be BD times EF. So this would just be BE plus DF. This would be my resulting matrix. As you can see, it is a 2 by 1 matrix. 1, 2, and then 2, or one column right here. Okay, well, what if I want to multiply a 2 by 2 matrix? Let's say I have A, B, C, D, and then E, F, G, H. I would have, I'd split this into another two row vectors, and this one I split into 2 column vectors. So I'd have AB times EG. Well, that's what my first element will be. I'll just call these specific vectors so I don't have to write them all out. I'll call this vector U, vector V, vector W, this is vector X. My first element will be the dot product of U and W. So U and W. And my second element will be the dot product of V and W. So V and W. Third would be the dot product of X and V, or X and U. You can see 2 by 2, 2 by 2. The inside terms match, and the outside terms are 2 and 2. And this is indeed a 2 by 2 matrix. So this works. Let's go over what a determinant is. A determinant is usually notated like this. As you can see, previously we had square brackets to denote a matrix, and now we just have lines to denote the determinant of a matrix. What's the determinant? Well, by definition, it's just A times D minus B times C. Now, just practicing this real quick. Say I have the matrix 2, 3, 4, 1. This would just be 2 times 1 minus 4 times 3. This would equal 2 minus 12. This would be negative 10. Now this is just the determinant of a 2 by 2 matrix. Determinant of a 3 by 3 matrix is much more complicated. This requires things such as dot product and cross product of 3-dimensional vectors. I know that sounds really complicated right now because we haven't even learned what cross product is, nor have we learned what a 3-dimensional vector is, but we will probably do that later. So now let's go over identity matrices. So the identity matrix for a 2 by 2 matrix, usually denoted by I, is 1, 0, 0, 1. Now, what does this mean? Well, we can graph this. Let's split this into 2 vectors. We have 1, 0, 1, 0, and 0, 1. Or this is x-axis, this is the y-axis. So this is what an identity matrix is. This has length 1, this has length 1. It's basically just two vectors, 2 unit vectors. Now what about a 3 by 3 matrix? Well, this is just 1, 1, 1, 0, 0, 0, 0, 0. You may have noticed something here. The diagonals of an identity matrix are always 1, and the rest of the elements are 0. Now, how do we graph this other identity matrix? It's 3 by 3. This is a 2 by 2. This is a 3 by 3. Well, I briefly mentioned a 3-dimensional vector. So I guess let's just break this up into 3 vectors, each which have 3 dimensions, you could say. So instead of looking at a 2D plane as we did in this first matrix, we need to look at a 3D space. So let's draw our 1, 0, 0 here. This is the x-axis. The y-axis is right here, which is 0, 1, 0. The z-axis is right here, which is 0, 0, 1. And each of these have length 1, just to, I guess, more clearly show the plane or the space. This is a right angle. This is a right angle. And then I guess I'll just label these axes as well. So this is what a 3 by 3 identity matrix looks like. Now, what's an inverse matrix? You might be thinking, what? Did you say inverse matrix? Well, I know what an inverse function is. F of x, inverse f of x. I know what that is. I do not know what an inverse matrix is. Well, an inverse matrix, the whole concept is pretty simple. You have a matrix A, B, C, D, or I could just call this A. A. This is matrix A. I multiply it with the inverse of matrix A, and I get the identity matrix. Now, what? How do I find what an inverse matrix is? How do I find that? Well, let's go over, I guess, an example. Maybe we can find out then. Say we have 1, 2, 3, 4, and I want to multiply this by the inverse matrix, which I'll just say W, X, Y, Z, and this is equal to the identity matrix, 1, 0, 0, 1. Well, I guess I'll just multiply these then. I have W plus 2Y as my first element. I have 3W plus 4Y. I have X plus 2Z. Then I have 3X plus 4Z. 3X plus 4Z. So this is the product, and this is equal to 1, 0, 0, 1. So I guess I just use systems of equations. W plus 2y is 1. 3w plus 4y is 0. I have x plus 2z is equal to 0. X plus 4z is equal to 1. So I'll just use systems of equations then. I can multiply this by 2. And this by 2. This gives us 2w plus 4y is equal to 2. And here we have 3w plus 4y is equal to 0. So using eliminations, we could just subtract these two. And we will get the first equation from the second equation. So this would be 3w minus 2w just gives us w. 4y minus 4y gives us 0y is equal to 0 minus 2, which is negative 2. So I guess we're just ending up with w is equal to negative 2. And now that we know w is negative 2, we can substitute that into this equation right here. So we have 3 times negative 2 plus 4y is equal to 0. Negative 6 plus 4y is equal to 0. 6 is equal to 4y, meaning y is equal to 3 halves. All right, we know y is 3 halves then. Y is 3 halves. And now let's do the same thing with x and z. So we multiply this equation by 2 and this by 2, and we will get 2x plus 4z is equal to 0, and then we have 3x plus 4z is equal to 1. Subtracting the same way as we did before, we have x is equal to negative 1. Sorry, x is equal to 1, positive 1. And we could just write that down right here, x is equal to 1. And then substituting x is equal to 1 into the second equation here, we have 3 times 1 plus 4z equals 1. Gives us 4z is equal to negative 2. Thus, z is equal to negative 1/2. Here we have z is equal to negative 1/2. Meaning the inverse matrix would just be w, w, x, y, z. W, x, y, and z. Okay, well, does that really help us? What can we see from this? Well, I see something. This is actually really hard to spot, but what's the determinant of this matrix right here? The determinant of 1, 2, 3, 4 is equal to 4 minus 6, which is negative 2. So if I know the determinant is negative 2, let's see if I just do 1 over negative 2, and then I multiply that by, I just switch these two terms around, so I have 4 and 1 instead of instead of 1 and 4, and then I negate these 2 and 3, so I have negative 2 and negative 3. I multiply these two, and I get negative 2, 1, 3 halves, and negative 1/2. Well, hey, that matches. I know I kind of exaggerated this a bit. It was really hard to spot this whole thing, but this is how you find the identity or the inverse matrix. So let's define this. We have a matrix A, B, C, D. The inverse matrix would just be 1 over the determinant of A times, we'll switch these two, we have D and A, and then negate the C and the B. And we know that A times inverse of A is equal to the identity matrix.